So 7.4 touches on exponential relations. So first what we're going to do is we're going to make a table of values for each of the following relations. Now we can see the whole board. Okay, so we have y to the x, 2 to the x, y equals 2 to the x, y equals 3 to the x, and y equals 1/2 to the x. So what we need to do when we make a table of values is we actually have to sub in like 2 to that negative 3. Okay, and we'll get 1/8. 2 to the negative 2, and we'll get 1/4. 2 to the negative 1, and we'll get 1/2. Okay, and then 1, 2, 4, 8, 16. Okay, now for the 3, and we're going to get 3 to the negative 3. That's going to be 1/27. 3 to the negative 2 is going to be 1/9. Okay, 1/3, 1, 3, 9, 27, 81. Okay, and the same here. 1/2 to the negative 3. Okay, if we flip this and made it positive, it would be 2 to the 3, positive 3, using our exponent rules, and that becomes 8. Okay, this would be 1/2 to the negative 2, but we want to flip and raise it to the exponent 2, and then we get 4. Okay, we get 2, 1. This becomes 1/2, 1/4, 1/8, and 1/16. Okay, so let's go ahead and graph these. I'm going to go up by ones. So not all of this will fit, but 4 and 16 won't fit. 3 and 8, 1, 2, 3, 4, 5, 6, 7. It's going to be 1, 2, 3 up here. Okay, 2 and 4, 1, 2, 3, 4. 1 and 2, 0 and 1, negative 1.5, and then it keeps going down. So this is what we get for the first equation. And then 0 and 1, 1 and 3, 2 and 9, that's way more up there. All right, there we go. Okay, and this is 1/3, and this is decreasing very quickly on that side. Okay, and then we have 1/2 to the x. So this will be 1, and then negative 3, 8, negative 2, 4, 1, 2, 3, 4, negative 1, 2, and then these are going to get smaller and smaller very quickly. Okay, so there are the 3 graphs. So let's discuss the 3 graphs. What is similar between the 3 graphs? Well, they all go through the point 0, 1. And they're all curve. Okay, they're not lines, they're not quadratics. And then they all have an asymptote at y equals 0. So they all approach y equals 0. Like that or like that. Okay? And how are they, what is different? Some are increasing, the first 2 are increasing, and then the last one is decreasing. And then the other thing that's different is they increase or decrease by different rates. So different rates. Let's call it of growth. Okay, we're going to get into that habit of calling it growth and decay. So growth is getting bigger and then decay is getting smaller. Okay, so what conclusions can you make? So I'll tell you, the larger, as the base gets bigger, so tends to infinity or gets bigger, what happens is that the function increases faster. Function increases faster. Okay, and we can talk about that right here. The greater the base, so when we talk about 2x versus 3x, and of course that 3 would be greater, I don't want to say the faster the curve, the We can say the greater the base, we can either say the faster the curve increases or the steeper. A lot of times though we use steeper when it's a line. So let's say the faster the curve increases. Okay, and when the base is a fraction between 0 and 1, the base is decreased, or the curve is decreasing. So that's where we have that decay. Okay, so now let's just compare a linear, a quadratic, and an exponential function. So for each of the following, so given y equals 2x plus 3, we're going to actually graph it, okay? So this is the y-intercept, so 1, 2, 3. And this 2 right here is the slope. So we're going to go rise, which is 2 up, run, which is 1 over. Rise, 2 up, run, 1 over. Okay? We can also go 2 down, 1 to the left. 2 down, 1 to the left. Okay? So we know that this is a line. So type of relation, this is linear. Okay? The x-intercept here is, well, the y-intercept's 3, the x-intercept is negative 1.5. And there's no asymptote, okay? That doesn't exist with a linear relation. Now, we know that the vertex is 3, 1. So we're going to go 1, 2, 3, 1. And we know that this 2 is positive, so this is going to be, A is going to open up. So we're just going to go ahead and open this up like this. This is just going to be a sketch. We know this is quadratic. Okay? There's no x-intercepts, so none. The y-intercept, I'm just going to do this algebraically. We're going to just sub in 0 for the x in order to find the y-intercept. So negative 3 squared is 9, 9 is 18, plus 1 is 19. So this point right here would be 19. Okay, and there's no asymptotes because this doesn't exist for a quadratic. Okay, and 3 to the x, we're going to plot that. So 0, 1, 1, 3, 2, 9. Okay, we know those coordinates already from the previous slide. So this is an exponential relation. The x-intercept, there are none because there's an asymptote at y equals 0. And the y-intercept is 0, 1. Okay, so just a little bit of a good comparison here between linear, quadratic, and exponential and what they look like. Okay, now let's look at some word equations. So, example, Ontario's population is projected to grow exponentially, okay, based on this relation. So P equals 11 million. So 11 million is the starting point, so that's the population when they made this estimation, okay? And then 1.0112, so we're talking about like 1.12% every year, and that's a growth because we have also like this 1 attached to it, so it's 100% as well. Okay, and P is the population, N is the number of years after 1996. So this is going to come into play, and we're going to have to calculate from 1996 being N equals 0, like that's the start time. Okay, so the first question is what is the population in 1996? So we know that the population in 1996, well, the start time is 0, right? So in 1996, no time has passed. This goes to 1. So our starting or our initial population is 11 million. Okay, and what is the projected population in 2031? Well, in order to calculate this, what we have to do is we have to figure out how many years are between 2031 and 1996. So I would go ahead and subtract those. 2031 minus 1996. 35. Okay, and that's all we have to do because it's at 1.12% annually. 1.0112 raised to the exponent 35. So 16,243,8 81. And there are no decimals because when we're talking about people, we can't have a fraction of a person. Now let's look at some examples and decide whether they're linear, quadratic, or exponential. Okay? And I'll just explain them out loud. So the amount of radioactive material becomes half of the previous after 214 days. Well, this is exponential because we would continuously multiply by 1/2 times 1/2 times 1/2, okay? Because there's that ratio. It becomes a ratio of its original after 214 days. Okay, the path of a soccer ball when kicked is going to be quadratic because it's going to go up and then it's going to go down. Okay, Ernie gets a $1 per hour raise every year from his employer. So this $1 per hour is going to be linear because this is adding to the slope. Okay, and Simone gets a 5% increase in her salary every year. So this is kind of like a slope, but this is actually going to be exponential because it's going to depend, her raise is going to depend on her salary last year, and it is going to be like times 1.05. It's going to be a ratio of what it was last year, which is 5%. So it's not the same every single year, like that $1 per hour. It's a percentage of last year's. Okay, the path of a rock thrown from a bridge. Okay, that's going to be quadratic. Again, it's going to go up all the way to a maximum and then down. And the value of a rare hockey card increases by 9% each year. Okay, as soon as we see that percent, we can think exponential. Because it's like a rate. Okay, the value of an item increases by 2% each year. Okay, so when we see 2%, it increases by that much. So it's going to be worth 100% of the original value plus another 2%. Okay, as a rate, so 1.02. The graph shows the value of the item over time. So could this, for A, it's like Suzanne says that this relation could be exponential, but also quadratic. Do you agree or disagree? Okay, let's talk about this. This could be maybe, if it goes like this, it could be looking like a quadratic, but when we talk about its the value of this item increases by a certain rate. So as soon as we talk about rate, we know automatically that it is exponential. Okay? So if we have a little clipping of one part of the exponential, it may look quadratic, but really pay attention to the details in the question. Okay? And now, taking a look at this graph, after how many years was the value 200? So locate 200 on the value, go over until we hit the graph, and then down. So I would say about 32 years maybe? 32 years. And that's just interpolation. We've done that since grade 9. Okay, the item's value can be modeled by this relation. And as soon as we see this relation, back to question 1, this is definitely exponential. Okay, C is the value, or the cost, right, in dollars after T years. So let's use this to see when is the value 200? Okay, 1.02 T. So we're going to divide both sides by that 100, and we've only seen this once in this unit so far, 1.02 to the T. What we need to do is we need to rewrite this 2 as 1.02 to some exponent. So this is when we get out our calculators, and we put 1.02 into our calculators, and we keep putting exponents in until it's approximately 2. So exponent 5 gives us 1.1. Exponent 8 gives us 1.17, so I'm going to go big. Exponent 50 is way too big. It gives us 2.69. Exponent 25 gives us 1.6. 30, 1.81. 40. Okay. So we know it's going to be between 30 and 40. Let's try 37. We're almost there. 36, 35. Okay. So if you put in 1.02 to the exponent 35, and that's trial and error, it's going to equal 1.999889, very, very close to 2. Okay, when we have the same bases, we drop the bases, and t equals 35. So we said about 32 years. The equation says 35, so that's pretty close there. Okay, and D, determine how long it took for the item to reach 300. Okay, so let's go 300. From the graph, I would say about 53 years. But let's actually sub in the 300 into this equation. Okay, we're going to divide both sides by that 100. So this is 3, 1.02 to the t. Okay, we're going to rewrite 3 as 1.02 because we need the same base. And I'm going to take my calculator. I'm going to put 1.02. We know it's going to be bigger than 35. It's going to be around that 53. So 53, 54, 55, 56. I would say between 55 and 56. So either one. Let's just put 55. Drop the base. 55 equals t. Okay? What's good about us having this graph is that we can approximate it first, this 53, and cut right to this 53, and trial and error from there.